Hi everyone, we're going to pick up right where we left off in Chapter 6, talking about thermochemistry. So when we last met, we were discussing thermal energy transfer and how to calculate it. So remember, we talked a little bit about the heat transfer equation, so Q equals C delta T, and some of the different forms. So Q equals mCs delta T, and Q equals NC delta T. So remember, the difference between all of these equations is the units that we're using for our heat capacity, which is our C value. So in this first example here, our C is going to be heat capacity, usually in units of joules divided by degrees C. And that means that our Q value is going to be heat in joules, and our delta T is going to be temperature in degrees C. So if that heat capacity, that C value, was given in joules divided by kelvins, then that means that our delta T would have to be in kelvins. So the equation we're probably going to be using the most in this class is this middle one here, Q equals mCs delta T. And the difference is that our CS is the specific heat capacity, and remember, the specific heat capacity is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. So if that's the definition of specific heat capacity, that means that our units for specific heat capacity are going to be joules divided by grams times degrees C. Remember, these equations are very unit driven. So if these are our units for specific heat capacity, all of our units need to cancel out, which means that, again, our Q is going to be heat in joules, temperature is also going to be in degrees C. But now we have this M value, and remember that M stands for mass, not moles, it stands for mass. And because our units are in grams, the units of C are in grams, that means that the units of M also have to be in grams. That's going to allow us to cancel out all of our units when we solve this equation. So the other version of this equation that we might come across is with this N. The difference is that this N is moles, which means that our heat capacity value here is going to be joules divided by moles times degrees C if our delta T is in degrees C and our Q value is in joules. So again, if our delta T is in kelvins, then that means that our C value should be in joules divided by mole times kelvins. And then all of the other units stay the same. So we always want to line up our units whenever we're using these equations. The other thing we talked about before we left is we talked about the energy of a system and the energy of its surroundings, and how the internal energy of a system is equal to the sum of the kinetic and the potential energy of all particles in the system. So remember, internal energy is E, capital E, and that's equal to the kinetic energy plus the potential energy. And we talked about this in class already. This is just a summary to review what we've already discussed. So we also know that energy is the ability to perform work, which is a force acting through a distance. And we know that energy that's not translated into work is going to be released as heat. So the way that we usually express that is our change in energy is equal to heat plus work. And again, we've discussed this already. So sometimes we want to figure out the internal energy of a chemical system. And if we want to do that, in theory, we have three different options. So options for calculating internal energy. So option 1, we could measure the work performed and the heat released and add them together. Option 2 is that we could force all of the energy to turn into heat and measure the change in temperature to figure out the internal energy. So if we don't have any work, then that means that all of the internal energy is heat. So we could force all energy to heat, measure delta T. Option 3 would be to force all of the energy to perform work and measure the work. So we have to figure out what exactly we're going to do here. Option 3 is really not practical. And the reason for that is because in all processes, some energy is going to be lost as heat. And that's due to the second law of thermodynamics, which we're going to go into much more detail in Chem 1020. So for now, we're just going to narrow that down to options 1 and 2. So clearly, option 2 is going to be the simpler process. We only have to measure one thing. So that's what we're going to do. So if we want to measure the internal energy of a chemical system, we are going to figure out a way to turn all of that energy into heat so we don't even have to worry about work. And that way we can just use the change in temperature to measure the heat of the system and therefore get our internal energy. And we actually already have a word for this, and that is calorimetry. And calorimetry is determining the thermal energy exchange between a system and its surroundings by measuring the temperature change of the surroundings. And I'll write that down for you. So, determining the thermal energy exchange between a system and its surroundings by measuring the temperature change of the surroundings. Okay, so that's what we're going to do. And so we're going to use this technique called calorimetry to find the internal energy of our chemical system. But remember, we only want the energy to be transformed into heat, so we have to come up with some way to prevent it from doing work. And we do that by keeping a constant volume. And basically, when we keep a constant volume, we're just not allowing any of the volume to expand, and that prevents work from being done. And that's what's going to allow us to focus only on the heat of the system. And so this technique specifically is called constant volume calorimetry or bomb calorimetry. Constant volume calorimetry. And again, it is called bomb calorimetry. And it's called that because when we hold our volume constant, that's going to cause the pressure to increase. And when we have that constant volume like that, is going to cause the pressure to continue to increase because there's nowhere for the pressure to be released. So think back to the last chapter when we talked about some of the gas laws and how pressure and volume are related. So in order to use constant volume calorimetry, we need to use some special equipment called a bomb calorimeter. Let's see if I can move this over. There we go. Okay, so this is our bomb calorimeter. So as you can see, we put our sample. Do I have a pointer? I do. So we put our sample over here inside of what we call the bomb. So that's the part that's being really pressurized. And it's going to be in an oxygen atmosphere. And the reason for that is because we're going to create a combustion reaction. And remember, especially those of you who are taking the lab for this class, we've seen combustion reactions already. And one of the requirements for a combustion reaction is to have oxygen. That's one of the reactants. So bomb calorimetry uses combustion reactions. To measure the internal energy of the combustion of a substance. So again, that's why we need to have oxygen in our sample chamber. So this is going to be our system, right? So our reaction is our system. Everything else that can exchange energy with it is the surroundings. So the calorimeter itself, which consists of the container and this water here in the outer chamber, that's the surroundings. And remember the definition of calorimetry, if we look back up to the top here. Oops. Let's see. So if we look back at our definition of calorimetry, it's that we are going to figure out the thermal energy exchange between a system and its surroundings by measuring the temperature change of the surroundings. So that's why we have a thermometer here in the water, because that's going to allow us to measure the temperature change of the water, which is part of the surroundings. And then we'll be able to use that temperature change to figure out the thermal energy of our system. So another important thing to note is notice we have the stirrer here, and that's because we want this water to be constantly mixing, because we want all of the heat that's being transferred to spread throughout the sample evenly so that we can get an accurate measurement of what that temperature actually is. So as you can imagine, we're going to be using a version of our Q equals C delta T equation. This one's pretty similar to the ones we've already looked at. So when we're using bomb calorimetry specifically, we have a special version of that equation, and that is going to be Q of the calorimeter equals C of the calorimeter times delta T. So this Q value is going to be the heat absorbed by the calorimeter So take a moment to think about that. If heat is being absorbed, do we expect our Q value to be positive or negative? So when we think about that, we know that our Q value should be positive because the system is, or sorry, not the system, the calorimeter is gaining heat. And then the C value is the heat capacity of our calorimeter. And notice that there is no M or N value included in this equation. That's because the heat capacity of the calorimeter already takes into account the mass of that calorimeter, so we don't really need to include it. It's kind of inherently accounted for in that value already. And then we have our delta T, which is going to be the change in temperature of our surroundings, which again is our calorimeter. And when we're solving these types of equations, there's going to be kind of like 3 basic steps we're going to follow, and this might be a little bit different every time depending on the details of the problem you're trying to solve, but for the most part, solving these equations are going to follow 3 distinct steps. So in general, your first step is that you're going to actually do this experiment, or somebody is going to do this experiment, and you're going to have to figure out the heat absorbed by the calorimeter. And you would do that using the equation I just wrote above. And then our second step is that we need to find a way to relate the heat absorbed by the calorimeter to the heat released by our reaction. So we already know that the Q of the system is equal to the opposite of Q of the surroundings, right? So remember that from one of our previous lectures. So because this is true, therefore, these 3 little dots mean therefore, our Q of reaction is going to be equal to the opposite of Q of the calorimeter. Because remember, do I have a highlighter? I do. No, that's not a highlighter. This is a highlighter. So remember, the system is our reaction, and the surroundings are our calorimeter. So that allows us to take advantage of this equation and use that in our calculations. And then for our third step, we can use that heat to figure out the delta E of the reaction. So that's going to be the Q of the reaction, which we just found in step 2, over the moles of our substance. And what this does is it puts the units of delta E into either joules per mole or kilojoules per mole. So clearly, if the problem that you're trying to solve asks for your answer in units of joules or kilojoules, you don't need to take this step, but much of the time when we're looking for delta E of the reaction, we want either joules per mole or kilojoules per mole, so in order to solve it, you need to figure out how many moles of substance you started with and then solve that division. So we're going to do an example problem here using those 3 steps. Ooh, I didn't know that could move. Okay. So here's our sample problem. So when 1.010 grams of sucrose undergoes combustion in a bomb calorimeter, the temperature increases from 24.92 degrees C to 28.33 degrees C. Find delta E of reaction for the combustion of sucrose in kilojoules per mole of sucrose. The heat capacity of the bomb calorimeter is 4.90 kilojoules per degree C, and the molar mass of sucrose is 342.3 grams per mole. So if you want to go ahead and pause the video for a moment to copy down this problem into your notes, and then we'll go through the problem. So something to note when we start, let's take a look at our units here. So what do you notice for units? Well, notice that for temperature, we're in degrees C. And then it's asking for delta E of our reaction. It wants it in kilojoules per mole of sucrose. So that means when we figure out how many kilojoules are released during this combustion reaction, we're going to have to divide that by the number of moles of sucrose. So it's asking us to find delta E of reaction in units of kilojoules per mole of sucrose. Then what information do we already know? We already know the increase in temperature of the surroundings. So we know that delta T of the surroundings it raises from 24.92 degrees C to 28.33 degrees C. We know that we have 1.010 grams of sucrose. We don't know the moles, but some other information that we do have is we do know that the molar mass of sucrose is 342.3. And if that weren't given, it does give us the chemical formula. So if it weren't given, we could solve for that. So the molar mass equals 342.3 grams per mole, so that's going to allow us to convert sucrose, grams of sucrose into moles of sucrose. And then finally, we also know our heat capacity of the calorimeter. So we know that our Ccal equals 4.90 kilojoules over degrees C. So again, notice this is in kilojoules, not joules. That's a little bit different from what we've seen in some previous problems. So for our strategy, we know that based on the information we have, we can solve for the heat absorbed by our calorimeter. And we know that because we already have this value and we already have this value. And then step 2, once we get that Q of the calorimeter, we'll be able to get the Q of the reaction, because the Q of the reaction is going to be equal to the negative Q of the calorimeter. And then step 3, we know that we want to do delta E equals Q of the reaction divided by moles. And in order to do that, we need to convert grams to moles. Okay, so there's our strategy, so let's solve the problem. So we have Q of the calorimeter equals C of the calorimeter times delta T. When we fill in those values, we have 4.90 kilojoules over degrees C times 28.33 minus 24.92 degrees C. When we solve that, our Q of the calorimeter equals 16.7 kilojoules. Notice because degrees C will cancel with degrees C when we multiply those together, so we end up in units of kilojoules. Also notice that this value we end up with is positive. That's what we expect because the calorimeter is gaining, energy. The energy is being released from the reaction and gained by the calorimeter. Okay, so that's our step one. We found Q of the calorimeter. So now step two, Q of the reaction is going to equal negative Q of the calorimeter. So Q of the reaction is going to equal negative 16.7 kilojoules. Okay, so step two was easy. We just put a negative sign in front of the Q of the calorimeter. And finally, for step three, delta E equals Q of the reaction divided by moles of sucrose. So I'm not going to show the molar conversion here, but I know everybody knows how to do that already. So when you convert grams to moles, you should get 0.00295 moles of sucrose So when we fill in those values, we get negative 16.7 kilojoules divided by 0.00295 moles. So for delta E, we get negative 5.66 times 10 to the third kilojoules per mole. That's how you solve a bomb calorimetry problem.